Hello, and a very warm welcome to, first of all, Jose, and to this series of high performance papers here at the NIBO at Next Journal Club, which I have called this. We are at the University of Copenhagen, where I am a professor in human physiology, and I have taken a focus here on a series of what I have called high performance papers. And here in the beginning, we will have just in a small picture here of Jose, both to the left and to the right. Very warm welcome, Jose.
Oh, thank you. Thank you for having me, Lars. It's a pleasure to be here.
Yeah. And we will specifically focus on this paper here, influence of body temperature on the development of fatigue during prolonged exercise in the heat. So the warm welcome is very in line with the title. And as we can see here, this is a paper that you published late in the last century, and which I find it quite fascinating. It has picked up a lot of attention, but it's also a high performance paper in my book, because I think it has changed some of the concept and understanding, and it's clearly a very a leading paper within the environmental physiology. But maybe could you take us a little through what was the background for this study?
Yes, thanks, Lars, for the introduction. Well, after doing the PhD in Austin, Texas, about dehydration and hypothermia, I went in 1994 to do a postdoc in Denmark, with the intention, particularly the intention of doing experiments during prolonged exercise in the heat, where cardio output was reduced and performance was faster, occurred faster. So the first experiments I was involved were experiments that Bodil, Bensaltin, and others were doing with heat acclimatization in wet heat. In 1994, they have published a paper that have been highly cited as well, with heat acclimation in dry heat, where they show that during repeated bout of exercise in the heat, fatigue occur at the same high temperature of 40 degrees. So they established that phenomenon. And then in 1995-96, we did the experiment with dehydration during prolonged exercise in the heat. And we observed that also under the condition of dehydration, fatigue occurred with high temperature, close to 40 degrees. But in that condition, despite the changes in physiological strain, cardio output decrease, and there was alteration in metabolism, it seems that hypothermia was the main factor accounting for the faster appearance of exhaustion. So we decided to do an experiment to isolate the effects of hypothermia, and that were in a series of experiments, and the paper include two different studies that were undergraduate projects.
And maybe we can even jump here to some of the results, because I think that illustrates the experimental setup that you did with manipulating with the starting temperature or the rate of the rise.
Yeah, so the first one here on the left, that figure illustrates the manipulation, where just by putting the participants, the highly trained cyclists, immersing in a water tank with different temperature, we could change the initial temperature. It was either around 36, 37, or 38. But then when it started exercise, a constant workload, approximately 60% of VO2 max, as you could see, the rate of rise in core temperature was the same, but fatigue occurred a similar around 40 degree esophageal temperature. Muscle temperature was slightly higher, but also consistently high, close to 41, and skin temperature 37.
Yeah.
on the right, illustrated follow-up experiment, we said, okay, so what happened is we change the rate of rise. Is we speed it up compare or slowing it down, does still fatigue occurs at the same level of hypothermia, and that was actually what happened with the high rise of heat storage. That was induced with a water-perfused jacket. Then fatigue also occurs at this high and similar esophageal temperatures. So that's set up that
was the two main experiments done.
Yeah.
When we see to the right there, when you slower the rate and so on, I guess it was also with a slightly lower skin temperature.
Yes.
Yeah. Do you think that's an interaction there? Because you can also see that it's a slightly lower core temperature that they end with, probably not statistically significantly different, but still, I mean, I guess when you have a lower skin temperature, then the cardiovascular stress may also be slightly affected. Or
yes, if it is well established that if you exercise in a cold environment or a hot environment, the same intensity, then you have a lower heart rate. So just having a lower skin temperature per se have some effects, cardiovascular effects that could interact. You mentioned.
And if we jump to the cardiovascular, because I mean, you have modified some of your figures here, and normally we take the original figures from the papers, but I know that you are very, I mean, your quality of figures has always been a benchmark for your publications, I guess. But here there are also some further figures illustrating how the cardiovascular response is affected.
Yeah, I just wanted to emphasize, because heart rate is the variable that everyone can measure and is regularly measured, particularly in cyclists. So to illustrate the point that despite the different core temperature, when you plot core temperature against heart rate in the two experiments, you find the same relationship. There's an increase of 14 to, in the first study, of 14 to 18 beats per minute per degree increase in core temperature, while in the other experiment it was similar also from 12 to 16 in all the experiments. So it's a highly reproducible effect, and that those data also are in a full agreement with experiments with an isolated heart preparation of Knowlton and Starling in the early 1900s.
In the paper, and I will, of course, suggest to people that if they find interested in this topic, that they dig into the paper. I also really like the figures where you plot against core temperature the changes in heart rate, skin blood flow, stroke volume, where you can see that as the core temperature increases, you have, of course, the increase in heart rate like here, but you also have the decline in stroke volume, and interestingly, the plateau in skin blood flow. So all of this interaction between these parameters. And how do you see this? Because I mean, people always take the approach that, oh, heart rate is going up because stroke volume is declining, so it's a compensatory mechanism. On the other hand, when you increase heart rate, I think people also tend to forget that then you also shorten the cardiac cycle. So the diastolic filling in particular is compromised. How do you see this interaction, and how important is that for the fatigue development?
Well, that is a basic question that have taken quite a lot of years in order to actually clarify. I remember those when we tried to publish those papers, we basically couldn't put forward the idea that heart rate could lead to reduction in a stroke volume. And it was because that could not be the case. Everything is related to the increases in skin blood flow. But then the experiments with pace in the heart have set light in this area and clearly demonstrate that if you increase heart rate just independently of all the other factors that increase venous return to the heart, then you don't change cardio output to peripheral blood flow. So heart rate, it is a good marker that indicates where you are close to fatigue or not. But those experiments with the heart rate pacing have demonstrated that it's not the cause of the fatigue itself.
No, and how do you see it in this one? I mean, because it could be now you have your last figure here that maybe we could jump to that, where you have also a little about the physiological strain and the different potential mechanisms that could provoke fatigue. And in this particular setup here, how do you see the changes that you illustrate here in the middle of the figure with the heart rate and its effect? Do you see it as a limiting factor in your specific setup here for oxygen delivery to the exercising muscles? So how do you see the cardiovascular stressing, so to say, here? What role does it play in the particular setup that you had in this experiment?
Okay, this figure belongs to a review where we try to explain the phenomena from multiple studies that have been done in the area where metabolism and cardiovascular responses and or thermoregulatory responses have been measured, not only during prolonged exercise, but also during maximal exercise. Based on evidence that we have scrutinized, we came up with a proposal that under those conditions where the phenomenon is very clear, if you go to these extreme conditions, environmental conditions, fatigue, it is faster when you are hypothermic. And so the basic question is, what is the cause of that fatigue? And that's what many experiments have been addressing, and I have followed up our paper. It is basically, our take is that the brain, there have been the hypothesis where the central drive is actually reduced, central drive to the muscles. And we actually, when you look at EMG activity in the muscles, if anything is going up, that's the only way that can happen is central drive is also elevated. Also, oxygen consumption in the brain, flow is impaired in the brain, but oxygen consumption is not. And the same applies to the respiratory system and also the heart levels. Yes, heart rate increases, but at the level of the heart as a whole, and the pacing experiment have demonstrated that there's not an impairment in myocardial VO2. However, at the level of skeletal muscle, and there is an area where we still need to do a lot of research to understand the recruitment and how we relate total energy turnover of the leg to muscle recruitment. But based on EMG activity during fatiguing exercise, if anything is going up, and under those conditions, there is a number of studies have shown that VO2 is either maintained or reduced.
But I guess that also depends on the exercise mode. Do you exercise with a small muscle mass, a large muscle mass? Is it maximal intensity? I mean, what factor becomes limiting of that?
Yes. You and others have followed up with those experiments where you have also looked at the local level. But it's also, it's also reproducible if you do knee extensor exercise or arm exercise, even in isolated conditions, you also will fatigue.
Yeah, for sure. Yeah.
That phenomenon is universal.
But I guess that can also be that the relative importance of the different factors that you sketch here can change.
Yes.
And I also remember that you, because I was co-authoring that one, wrote an editorial where you said that this critical core temperature, because I mean, if we look at the data, especially the first figures up here, people could get the impression that, 40 degrees, that's so to say a critical temperature. But I guess that is in the conditions where you have this specific environmental conditions, you have this intensity and so on. If we took the same subjects and instead of having it at 60%, but it was 80% or it was 40% or different humidity, then maybe the core temperature at the end would be slightly different.
Yeah, precisely. Yeah, in those conditions, basically, this study was a proof of concept that hypothermia can cause, in certain conditions, may be a primary factor causing fatigue. We didn't identify the precise cascades of events leading to that. And there have been more studies, and you did those, the involvement of the brain.
No, and also, as you said, until you have the pacing or you can isolate a certain factor, then you can also see very high correlations to blood temperature. You can see very high correlations to heart rate and so on, and then you have to pinpoint it out. And that's, of course, also always the challenge when you do these, you could say, intact human integrative studies and so on. But I think that this study, I mean, for the first time, you could see, okay, now you see the same pattern as you see with the repeated exposure during acclimatization, and you can see, okay, and now you then manipulated it. So I think this was an elegant first step in order to identify that hypothermia, so to say, per se, is a fatigue eliciting factor. Then you can, of course, say through which mechanism does it then provoke it. But I also see that there was I mean, from all of the 1,500 papers now that have cited this paper here, I mean, some of them, and surely a lot of my time has been taken up by trying to identify, okay, what is then the role of different, the muscles, the cardiovascular or the central nervous drive to this perspective. But I think that was where it, so to say, paved the road for a variety of studies across, I mean, our labs in Australia, North US, and so on. And how do you see these papers? I mean, have we gotten closer to understand the mechanisms, or is it still that, well, hypothermia causes fatigue? And
yeah, but I think it has been very excited to see the development of the area, because to me, as a whole, it has demonstrated how reproducible in these extreme conditions the phenomenon is, and also even in outdoor conditions, you still find that the fatigue occurs with this high temperature. And there have been people have been very creative in trying to cool different areas of the body to try to identify the mechanism. We're still not only in this area, but in general, in area of fatigue, we still have to understand more about recruitment of muscle and the relation to metabolism and temperature to pinpoint more the mechanisms. But definitely, there's a clarity that we didn't have in the 1990s in regards to the consistency of the phenomenon.
No, but I think that besides changing or affecting how science has studied this, I think in practice, I mean, we see all in the Tour de France, etc. I mean, they have ice packages. Every half an hour, they put ice packages in order to prevent hypothermia. And I think that this, I mean, whereas in the old days, we all said, oh, when you get fatigued and so on, it's dehydration. And of course, there can be a lot of interaction, because if you get hot, you sweat more, you become more dehydrated. And the other way around, as you also have demonstrated, if you become dehydrated, the risk of developing hypothermia increases. And you can say cooling with the ice packages, which has become practice, I mean, all over, ice vests and so on. I think this whole plethora of both practice and studies have changed. And you can say, of course, maybe it's not one paper changing it, but I think that this paper was, so to say, a changing point in really focusing on that aspect.
Yeah, I think there's still further work that needs to be done in the translation of this basic concepts to performance at some time. But by looking at the time courses the appearance of fatigue or the core temperatures. And so it's very important. For example, in the Olympics, there was this idea, oh, we have to cool down the athlete very quickly. And if you look at how fast temperature declines, you realize that within 10 minutes, you can have core temperature down from close to 40 to 38 or below. So it is important to do more experiments that allows us to make the specific recommendations, because sometimes, like doing intervention like pre-cooling and so, they come. There's like anything, there's trade-off. And
it's also quite funny that in you could say for acute performance to prevent fatigue, then it can in these conditions be advisable to avoid, pre-cool, cool down afterwards, or per-cool, cool during. But in order to achieve the adaptive effect, then there's some quite showing that, okay, then you might need to get to the higher core temperature. There's also actually some that the outcome of strength training can be reduced if you cool immediately afterwards. So one should always discriminate to say what is the effect for a given condition. You're going now to do your best performance in this. It was 40 degrees in the experiments you did, wasn't it? So on. Yeah. So we always use the quite extreme, but that becomes normal, and several venues have this conditions and so on. But then you could say, okay, in order to achieve the adaptive effect or the training effect, then you will actually do the reverse. You will superimpose heat stress in order to get some of these adaptations. But that's in another line, but it's just to discriminate between acute performance fatigue and the adaptive response during training.
Definitely it is an area now where it's attracting a lot of interest. Actually, the effects of heat training, but then not only in elite athletes, but also in disease populations, in the elderly.
Yeah,
so it is an area of great interest.
Yeah. So today, what is your main experiments that you're doing within this area? Are there some related where you are exploring some of the mechanisms, or how has it gone?
Yeah, I think it is actually, we are also following up this basic idea during maximal exercise. There's an idea that if you exercise in the heat, your skin flow might actually decrease. The prediction is the decrease. And so we're actually doing experiments doing incremental exercise, prolonged exercise, and repeated maximal exercise to look at directly measuring skin blood flow. So there's this dogma that if you exercise in the heat, you can have skin blood flow of 7-8 liters. But this is an area where we need to actually be able to quantify how many liters. It's an estimate based on changes in cardio output and estimate of changes in visceral flow.
So you still have a large focus on the cardiovascular changes and how they interact with temperature regulation. So
but also we have a lot of interest in just looking at the effect of temperature locally in just the leg, on an area of the leg, and just more on the blood flow regulation.
Yeah, because in this particular experiment that you did here, all of them increased in parallel. So when the core temperature goes up, then you will, of course, also, because a lot of the cardiac output goes to the exercising muscles, then they will increase in parallel, always being slightly higher. Your brain temperature will increase in parallel, and so on.
So this is what is important, try to understand the phenomenon, and you establish at the whole body level, but at the same time you have to go down to a smaller exercise model, or sometimes just limb model, to try and then come back again. So there is a lot to learn from that type of complementary approaches.
Yeah. So, but what I can do to the listeners of this is really recommend to dig into the paper. There will be a link directly to the PDF of the paper and dig into it. And what do you think now that when people read it, what should they especially be aware of, and what is, so to say, the take-home messages from this paper and what has gone beyond?
I think the take home it is that the data clearly supports the consistency of the phenomenon of the hypothermia in relation to fatigue. So that's a consistent, but people should be as you pointed out before, be aware of the conditions, environmental conditions. Don't try to extrapolate those findings to every possible condition where athletes will compete. But the phenomenon is highly consistent, but it's a phenomenon of these changes in temperatures associated with changes in many other physiological systems. So from an integrated viewpoint, it's important to consider the responses of the other system and don't take for granted that a correlation it is indicative, of course. So you have a higher correlation with heart rate, and this is the cause of fatigue, for example. A high correlation with rating of perceived exertion, so it's rating of perceived exertion which causes fatigue.
No,
so
but that is still a really good factor. I mean, if you want to know some people and what is the risk of them dropping off the bike in the next, I mean, the RPE is always a good measure.
Yes, no doubt. In regards to the applicability of how close you are to fatigue, yes, it is fantastic. Yeah. But to explain the phenomenon, what is
and the underlying mechanisms.
That's it is. Then you have to try to isolate those factors. So that's I think it is important take-home message. I think that will allows us to progress further in this area of understanding, how the body works.
But still, the most effective mechanisms then in preventing the fatigue, that is to avoid the hypothermia. Because if you avoid the hypothermia, then you also avoid the entire cascade of cardiovascular strain changes, effect on the brain, and so on. So, I mean, you could say from an overall, if you're a performance physiologist or a trainer, I mean, then you could say, okay, avoid the hypothermia, and then you are getting rid of a lot of the problems.
Well, yeah, and those experiments was very clear when you have a controlled condition where the same people, exercise in a cooler environment, you're in a hot environment, but you put a cool...
but also in your pre-cooling, I mean, just cooling them ahead of it. And you can say that is where maybe there's a discrepancy between what you can do in a lab experiments. People start with a steady pace output, whereas if you were a marathon runner and you pre-cooled too extensively, then maybe it could also affect your running in the first, so there's also some when you translate from the lab to the practice, then there may be some trade-off or you could say translation of the results. I mean, we see today that many athletes, if they are going into conditions where the risk of developing hypothermia, I mean, then they pre-cool. Maybe not the entire body as you did here. You did water submission, or how was it for the and then maybe it may be only ice vest, or it may be located cooling in order to avoid some of the direct cooling of the muscle if you need to have a fast start. I mean, because here in these conditions you started at a submaximal exercise intensity.
It's also if you are like a cyclist now warm up for a time trial in front of a big fan. That's also very helpful in maintaining a lower.
For sure. Or you could say avoiding to develop hypothermia before you initiate, just like when you preheated people. So it has affected practice and it has affected science, and I think that it was a wonderful take through this article. So I think I will round up here by thanking you a lot for taking your time and participation to this series of high performance papers, which has an originality from our institute here from the last century, with you visiting us and contributing to science. So many thanks for your visit here at the podcast, Jose.
Thank you, Lars, for having me. It has been a pleasure.